Okay, so for you've got this like on your slides. So according to the reaction where we have hydrogen and iodine and 52 kilojoules of energy is going to react to give us two hydroiodic acids. So how many kilojoules would be absorbed if 6 moles of iodine gas are reacted? So for this, we have 6 moles of our iodine. So again, we're going to write down what we have. We've got 6 moles of our I2. Okay, we want to get to kilojoules this time. So all we're going to do for this is, again, we're going to drop it like it's hot. And so we've got moles of iodine, I2 here. We can treat our energy like any other reactant, but for this, because it's being added, we're going to say that our delta H is a positive 52 kilojoules. So this is the number that we can then put in here to calculate if we had 6 moles instead of 1, what would happen. So if we go 6 times 52, we end up with 310 kilojoules. And if we're looking at sig figs, we'd only have 1. So really, if we're being super specific, it would be 300. It's early. 300 kilojoules. Okay, so again, you're writing down what I'm writing down. So if you need to pause the video, you're doing that right now. Okay, so this is a different type of reaction. So based on if we have 2 ammonia breaking down into nitrogen, so 1 nitrogen and 3 hydrogen, it's going to take a positive 92.4 kilojoules. So for this, how much heat is absorbed when 68.0 grams of ammonia, this is NH3, decomposes. So if we go 68.0 grams of our NH3, again, we're asked to find our heat. So we're looking for kilojoules. Can we go from grams to kilojoules directly? Absolutely not. When in doubt, solve for moles. Okay, so you've got grams, your NH3, and your 1 mole of NH3 here. Okay, so again, this is coming from the periodic table. So you've got 1 nitrogen. If you look on the periodic table, the molar mass of nitrogen is going to be 14.01. Hydrogen, 3 times our 1.01 gives us our 3.03, our 14.01. If you can do this in your calculator by itself, that's even better. So we would have a molar mass of 17.04 grams. Okay, so now we can get rid of our grams of ammonia. We've got our moles of ammonia right here. So now that we've got moles of ammonia, we can drop it like it's hot. So we've got moles of NH3. We want to get to kilojoules again, so kilojoules can go on top. Our heat of reaction over here is our 92.4 kilojoules. It's going to be positive 92.4 kilojoules for every 2 moles of ammonia that's used. You can cross it out. So same as always, when we drop it like it's hot, you're going to multiply across the top. So you've got your 68.0 times 92.4 times 1 divided by 17.04 divided by 2 gives us 184. So here we had 3 sig figs. If we're looking at our answer, we'd have 1, 2, 3. That 3 is going to round down, so it'd be 184 kilojoules would be our answer. Okay, so if we're looking at this example, we're told that 2 moles of ammonia plus 1.5 moles of oxygen is going to react to give us 1 mole of our nitrogen plus 3 moles of our water. Okay, and our change in enthalpy for this is a negative 76.5 kilojoules. So if we have 4 moles and 3 and 2 and 6, there's a couple different things that we could do. So we could formally solve it by drop it like it's hot, or we know, hey, you know what? We had to go 2 times 2 gave me that 4. 1.5 times our 2 gave me the 3. Or my 1 times 2 gave me the 2. My 3 times 2 is going to give me the 6. So because I multiplied everything else by 2 to get down to here, I need to multiply this part by 2 too. I guess we could do it like this. So to find my change in enthalpy for this, I'm going to go 2 times my negative 765 is going to give me negative 1,530 kilojoules as my answer. Okay, so this, again, just as extra practice, it's an exothermic reaction because it's negative. We haven't done anything to it, so this would be an exothermic reaction too. We look at this one. Things get a little bit more complicated, but it's all good. So here, we have 2 carbon dioxides. We have 3 waters. We've got reacting to give us 1 over CH3, CH2OH. If you're wondering, this is ethanol plus our 3 oxygens. This is an exothermic reaction. It is negative 1,367 kilojoules. So there's a couple different things that have happened here. Starting with, we have ended up flipping our reactants and our products to get down to here. So if we can rewrite it out, so there's C3H2OH plus our 3 oxygen. So this is a liquid, this is a gas. Change, we've got 2 carbon dioxides, gas plus 3 H2Os as a liquid. So here, it was like we had 1,367 kilojoules as a product. And so really that ends up getting brought over here too. Okay. How we end up showing that is that our delta H, if it's a negative with the reaction, we end up switching them, switching our reactants and products. This is going to become a positive 1,367. Okay. So now all I've done is I've multiplied by 4 to go from my 1 to my 4, 3 times my 4, my 2 to my 8, 3 again times 4 to get there. So I'm going to need to multiply this by 4 as well. So if I go 1,367 times 4, I end up with an answer of positive, okay, because my reaction has switched. So it started off as an exothermic. It has now become an endothermic, which is why I've got my 2 positives, 5,468 kilojoules. Your practice sheet is going to be this. So the first thing that you need to do is you need to tell me whether or not it's an exothermic or an endothermic reaction. Okay, so this one's, I like to throw you for a loop to start. Okay, so this liquid, do we have to add energy or take away energy to get it to a gas? Well, we need to add energy, right? So you could put add energy here, and either way, your first one's going to be endo, and then you're going to look, hey, this is a negative. You can look all the way down. You're going to tell me how you know, okay? You know by you're looking at the symbol of it. So for question 2, what is the value of delta H for the following reactions? Use above questions for help. So you're going to use these. You can either tell, like for this, you're just telling me whether or not it's exothermic or endothermic, but for these other ones, you're going to look and tell me what's changed between these two. Okay, so for our B, our reaction has, like our reactants and products have switched places. So for this, you would tell me that, hey, my delta H is going to be a positive 72.4 kilojoules. Okay, these questions at the bottom. So how much energy would be released if 33.0 grams of sulfur dioxide reacted? So you can either use 1C or 2C. Again, this is like those calculations that we did at the start of the video. And then this is solving backwards. Let me know if you need any help. There's also questions on the back of the sheet that can be done as well.